Alright, so with z-scores, we need to make sure that whether we are dealing with a sample or with a population that we use one of the two formulas, we're basically doing the same thing though. We're taking some value of x that we're comparing maybe some set of data with, and we're subtracting the mean and dividing by the standard deviation. It's the same thing in the other formulas, just different symbols. Same stuff. Okay. Make sure that if you round a z-score, and you do want to round a z-score, that you round to 2 decimal places. Very important. The reason for that is there are certain tables that we'll use z-scores with, and they have 2 decimal places. Okay. All right. So how can we use z-scores to measure relative standing? I'm going to read through this example real quick. All right. So let's consider a comparison of 2 individual data values with this question. Which of the following data values is more extreme? A Chips Ahoy cookie with 30 chocolate chips, and then it tells us the mean, it tells us the standard deviation, or a regular Coke with a weight of 0.8295 pounds. And again, it tells you a mean and it tells you standard deviation. So it wants to know which one of these two would be more extreme. All right. The way we can do that is by converting each value over to a z-score. So that's what they're doing down here with the given information. First, they're looking at the chocolate chip cookie with 30 chocolate chips. So the 30 chocolate chips, that's the x in the formula. Minus x bar, that's the mean. How many chocolate chips on average did each chip have? It was 24.0. The standard deviation for the set of data was 2.6. And they come up with a z-score of 2.31. They did the same thing with the can of Coke. They knew how much the can of Coke weighed. They subtracted the mean and they divided by the standard deviation. And they got a z-score of 1.69. So the larger of the two will be the more extreme value. Look at the interpretation. The results show that the cookie is 2.31 standard deviations above the mean, and the can of Coke is 1.69 standard deviations above the mean. Because the cookie is more standard deviations above the mean, it is the more extreme value. A cookie with 30 chocolate chips is more extreme than a can of Coke weighing 0.8295 pounds. Alright, now, so how do we know if these would be ordinary values that we could expect to get, or usual and unusual values? We went over that with standard deviation. To find the maximum usual value, you say the mean plus 2 times the standard deviation, and to find the minimum usual value, you say the mean minus 2 times the standard deviation. Well, what if we already have the z-scores? For z-scores, you can think about a number line with all the z-scores on it. Okay? Right here in the middle, we're going to have a z-score of 0. This is where the mean of the set of data is. All right? If you are up to 2 standard deviations, up to the number 2 for your z-score, or you're at the number -2 for your z. So if your z-score, what I'm saying is if your z-score is between -2 and 2, those are considered to be usual or ordinary values. If your z-score is greater than 2, so any number greater than 2, or any number less than -2, then that means that's said to be an unusual value. So if the question would have been, is it usual or unusual to find 30 chips in a Chips Ahoy cookie? Look back at the z-score. It's unusual because the z-score is larger than 2.00. If we wanted to know, is it usual or unusual to find a can of Coke with a weight of 0.8295 pounds, the z-score was 1.69. That's between negative 2.00 and 2.00. So that's usual. All right. Let's look at maybe a problem from the back of the section. That was example. Yeah, that was example number 1. Compare and count. Comparing a count and a weight. It does refer back to example 8 in section 3, but it was example 1 on page 126. All right. Let's look at, how about we look at number 7 here. Job. When Steve Jobs was chief executive officer of Apple, he earned an annual salary of $1. The CEOs of the 50 largest U.S. companies had a mean salary of $1,449,779 and a standard deviation of $527,651. What is the difference between job salary and the mean CEO salary? So if he was only paid $1 a year, he must have been a pretty well-off individual to accept that type of salary. But what's the difference? Okay. So we say 1 minus 1,449,779. Okay. So that's the difference. 1,449,778 negative. Now, how many standard deviations is that? You divide the number of standard deviations. What we're doing here, these steps are just stepping you through finding the z-score. So 527,651. That's how you find how many standard deviations that would be. Now, part C says convert his salary to a z-score. Well, that's what we just did. We said x minus x bar, and we're dividing by the standard deviation. So that's what we do. That's what we're doing. All right, so that's this big number divided by 527,651. So that's, if we rounded that to 2 places, that would be negative 2.75. If we consider usual salaries to be those that convert to z-scores between negative 2 and 2, is Steve Jobs' salary usual or unusual? It's unusual because it's less than negative 2.00. Okay. Again, these steps in this problem, they're just, the first one and the second one's just stepping you through how to find the z-score. Step 3 says convert it to his salary to a z-score. Well, that's what we were doing. And so we found the z-score to be negative 2.7 whatever, and that was less than negative 2. Okay? So it's really easy to find a z-score. Not hard at all. Okay? Now let's look at percentiles. If you can think back to taking standardized tests, whether it was recently the ACT or some type of standardized test in high school, a lot of times when you get your results, you'll see maybe you scored in the 20th percentile or the 80th percentile. What does that mean? Well, percentiles are measures of location, denoted piece of 1, piece of 2, all the way to piece of 99, which divide a set of data into 100 groups with about 1% of the values in each group. So let's say that I had a group of 30 student tests. A percentile, if I say that you scored in the 75th percentile, then that would mean if I took all of those 30 tests and I divided that into 100 groups, then you made better, or you made higher than, or right at 75% of the group. There are 25% that made higher than you, but there's about 75% of that group that made either what you made or lower than you. So how can we actually find those values? How can we find what the 20th percentile would be? What number would that be at in the set of data? Or what the 75th percentile would be? There is an actual method that we have to go through to find what number a percentile corresponds to. Alright, but you have to have the set of data to do that. Now there's a good figure in your book and that figure gives you a step-by-step breakdown of what you do to find a percentile. Alright, it's figure 3.5. What it says do is first sort the data, lowest to highest. Now then, if we want to find a percentile, like say the 40th percentile, say we wanted to find the 40th percentile, well that's P sub 40. That means 40th percentile. To find this, we have to first figure out something called L. And L is equal to whatever the percentile is divided by 100 times n, the number of items in your data set. So we don't know how many items are in a set. I haven't looked at a set of data. But if I want to find the 40th percentile, I do know that I have to say 40 divided by 100 and then times ever how many data items are in the set. That's going to give me some value that we call L. We'll use that value to figure out where the 40th percentile is located. Okay? So let's do that for some set of data. Again, we're going to use this chart right here. And the chart tells us to first arrange the data, then we're going to find this term, this variable L, and then I'll show you what to do from that point. Alright, so let's say that we have a set of data from page 193. Let me go to that in your text real quick. And here's the set of data I'm talking about. I'm going to go ahead and clip that set of data out real quick. Alright. Alright. I don't believe we'll need any of this right now. This is how to figure out what percentile you're at, these numbers. So we'll get back to those in just a second. What we're trying to figure out now is how do we find where the 40th percentile is. Okay, so let's say I wanted to find the 40th percentile, since that's what I was doing earlier. These data items, have they been sorted least to greatest? Yes. Okay. All right. So 9 point what?
9.6.
Okay. All right. So how do we find piece of 40 or the 40th percentile? We first find L. You find L by saying whatever percentile divided by 100 times the number of data items in the set. There are 24 up here. So 40 divided by 100 times 24 is 9.6. If you get a decimal, you round up. So it doesn't matter if this was 9.1 or if this was 9.6. It says to round up. So we want to look at the 10th term in the data set. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the 40th percentile is 243. Okay. Let's do another. Let's find the 70th percentile. All right, so first we calculate L. L is 70 over 100 times the number of data items, 24. So 70 divided by 100 times 24, 16.8. So round that up, that's 17. So there's 12 here, so that's the 12th, 13, 14, 15, 16, 17. So the 70th percentile is 254. What does that mean? That means 254 is the 70th percentile, or the value that separates the top 30% from the bottom 70%. So if you score in the 70th percentile, then that should be pretty good, because you're right there at, the top 30%. I think it should be pretty good. It should be acceptable if you're talking about grades or something like that. Let's see if we can do one more, maybe one that will come out with a whole number. Let's do the 60th percentile. All right, so if I find the 60th percentile, first we need to find L. L would be 60 over 100 times 24. Yeah, 60th is still going to give us a decimal. What was it?
50.
Now, what was this? Let's see.
14.4.
So we might as well finish this one. 14.4. Oh, well, this is a good example of, even though this is 0.4, we still round that up to 15. It's not. It doesn't say just round. We round up. So this would be the 15th term. So 251. Let's try the 50th percentile. All right. So it's going to be 50 divided by 100 times 24, or 12. When you get a whole number like that, our table says, or our figure here, if you get a whole number, the value of the kth percentile is midway between the nth value and the next value. So that means that we're going to go to the 12th value, which is right here. We're going to take the 12th value and the 13th value. We're going to add them together, 250 and 245, and divide by 2. All right, so 250 plus 245 divided by 2. So 247.5. All right, and that's what P sub 50 is, or the 50th percentile. Even though that data item isn't there, that's how we find the score that would separate the top half from the bottom half, or the top 50% from the bottom 50%. Okay. Now, what if we have a number and we want to know what percentile that is? So, for example, what if my number of this data, and I don't know what type of set this is, I didn't really read the directions, but what if my number that I was given was 235, and I want to know what is the percentile that corresponds to 235. Looks like these are seconds, so it doesn't matter. So what we do is we say, or we need to count up, sorry, to the position of 235. So which position is that? We have 1, 2, 3, 4, 5, 6, 7. So it's data item number 7. How many data items are there? 24. So you divide by 24 and say that times 100. That will tell you what percentile that number is located at. So 7 divided by 24 times 100 . Okay. So what do we say that was? 29%? 29.16%? Alright, well, that's not really the typical way that you would use a table like that. Let's just pretend that we have this table here, and we want to know, these are all seconds. Say this was the number of seconds you could hold your breath. How neat of a table would that be? You know, if I could hold my breath 110 seconds, I'd probably be, you know, if I practiced, I could probably do that. It'd take a while. You got to, you know, expand your lungs and practice a little bit. I don't know if I could do 273. That sounds like a little too extreme. But there's a good chance that my number wouldn't be one of these items up here, right? So here's more or less how this would be used. Say that I could hold my breath 200 seconds. That's a pretty long time. So what if we want to know what percentile we would be at if we could hold our breath 200 seconds? Now the number 200 is not up here. What is up here though? These are arranged from least to greatest. So 200 would be right here though, wouldn't it? How many items are less than that? 3. So we say 3 divided by the number of data items times 100. Okay? Let's see. So what is 3 divided by 24 times 100? That's what? Is that how many we had less than? What was that? 1 point? Multiplied by 10. Alright, so multiply by 100. Get 12.5. So that's the percentile that you would be at. Okay. I guess you could say that we were in the bottom 13% because we got a decimal. But usually, you know, and that's how you would calculate your percentile. But usually it's the other way around. That's why the other way is so much different, is that usually if you have a data item, or I'm sorry, a percentile number, like you want to know what the 50th percentile would be, or you want to know what the 75th percentile would be. Okay. Now, the 25th percentile has a special name. The 50th percentile has a special name. The 75th percentile has a special name. Okay? Those values are actually can be called quartiles. This equals the 25th percentile equals the first quartile. All right, the way that it's written is Q sub 1. The 50th percentile, or that's also the median, by the way, that's the second quartile, or Q sub 2. And P sub 75, that's the third quartile, or Q sub 3. It's just that they have a different name. There are a couple of other terms that sometimes can be used in statistics with quartiles. Let me show those to you real quick. They're on page 132, I believe, of your textbook. You may see these statistics included in some reports. The inner quartile range, and the way you get that is just you say the third quartile, whatever that number would be, minus the first quartile. The semi-inner quartile range, the third quartile minus the first quartile divided by 2. The mid quartile, Q sub 3 plus Q sub 1, the third quartile plus the first quartile divided by 2. And then the 10 to 90 percentile range, the 50th percentile minus the 10th percentile. All right, and that's getting a little deeper than we'll actually have to go for quartiles or percentiles, but those are just some other statistics that may be included in reports or journals. Now we can use the minimum value, the maximum value, and the quartiles to do something called a box plot. All right, most graphing calculators will do a box plot. It's just that usually we don't use calculators to do stuff like that. The way that a box plot is set up, let me show you real quick. We have to know these values of the set of data. You have to know the minimum value, you have to know the 3 quartiles here, and you have to know the maximum value. All right, once you know those, then whatever that number is, whatever these numbers are, the way that we do a box plot kind of looks like this. It's kind of like a number line. It has a line on each end. Right here, the number that goes here is the minimum number. The number that goes here is the maximum number. All right, then you're going to have some number at the first quartile, some number at the second quartile, and some number at the third quartile. That's Q sub 1, Q sub 2, and Q sub 3. And you can make a box around those 3 points. Okay? And all these will be numbers. It's just a way to graphically show the minimum, maximum, and the 3 quartiles. Let me show you a picture. It's on page 133. Well, here's one on the next page. Or this is one on 137. For whatever set of data, well, here's the set of data right here with the quartiles, it looks like. So the minimum value in the data set was 5. The maximum was 380. The number at the 25th percentile, which is the first quartile, was 47. The number at Q sub 2, or the median, was 104. And the number at the third quartile, or the 75th percentile, was 121. So they put those on a number line, and then they drew a box here, and that's what it would look like. Okay. Any questions about a box plot? They're not going to be used a lot in here. I just want you to understand what they are and how to make one. You have to do the work to find the quartiles, the first quartile, the second quartile, the third quartile. Then you have to identify the minimum and maximum value, put all of those values on a number line, and then draw your box over using the first quartile, the second quartile, and the third quartile.